Good afternoon. Today we're going to be talking about section 4.3, what derivatives tell us. And this really leads from an example I did in 4.2 where I graphed my function, and it gives us a few more tools for graphing functions. And section 4.4 is indeed, how do we graph functions using the derivative? So this section really prepares us for that. So let's talk about increasing and decreasing functions. Suppose a function f is defined on an interval I. We say that f is increasing on I if f of x2 is greater than f of x1 whenever x2 is greater than x1. So that means to say that if I pick a point x2, which is greater than a point x1, and the function evaluated at that point is greater than the function evaluated at x1, then my function is increasing. And we can see this pretty clearly. This is the definition of increasing. So if there's increasing, there better be decreasing. Suppose a function f is defined on an interval I. We say that f is decreasing on I if f of x2 is less than f of x1 whenever x2 is greater than x1. So if I pick x2, maybe it's 5, and I compare it to x1 and 5 is greater than 1, then f evaluated at x2 better be less than f evaluated at x1. And that's how we know we've got a decreasing function. So if the graph of our function goes down towards the x-axis, or if it crosses the x-axis and continues going down towards negative infinity, we say we have a decreasing function. So how do we compare that to what we know about derivatives? And this is where theorem 4.7, the test for intervals of increase or decrease, comes into play. So suppose that f is continuous on an interval I and differentiable at all of the interior points. That's the same as saying it's continuous on the closed interval and differentiable on the open interval. If f prime of x is greater than 0 at all interior points of I, that is, our derivative is positive, then f is increasing on I. If our derivative is negative, that is, f prime of x is less than 0 at all interior points of I, then f is decreasing on I. So how do we use this to our advantage? Well, we start with an example. Find the intervals on which f of x equals 2x cubed plus 3x squared plus 1 is increasing and decreasing. So our first step is we need to divide the real number line into some intervals. So first we take the derivative of our function and determine the critical points. And the critical points occur when f prime of x equals 0, and that happens at x equals 0 and x equals -1. So now we split the real number line into 3 intervals, from negative infinity to -1, from -1 to 0, and from 0 to positive infinity. Or this is the same as finding the zeros of our function. So we could have figured out sorry, this is not the same as finding the zeros. Please disregard that. So we found the critical points of our function, and we used those critical points to split up the real number line into 3 not equal parts. Now we test points within our intervals to determine the sign of the derivative, and thus if the function is increasing or decreasing. So we start with the very first interval, which is, let me write my intervals again. Negative infinity to -1, -1 to 0, 0 to positive infinity. So for my first interval, negative infinity to -1, I pick x equal to -2. I plug in f, -2, into f prime of x, and I get 12. 12 is greater than 0, so f must be increasing from negative infinity to -1. Now I test my middle interval at x equals -1/2. I just picked a point, it could be anything. F prime of -1/2 is -3/2, which is less than 0, so f must be decreasing on this interval. At x equals 1, which is within the interval 0 to infinity, f prime of 1 is equal to 12, which is greater than 0, so f is increasing. So I get something that looks like, this. Increasing, decreasing, increasing. And I know from cubic functions that they're shaped like this. So it makes sense that I've got a little bit of a function increasing and then decreasing and then increasing again. So now we come to something called the first derivative test. Let f be continuous and differentiable on an interval that contains a critical point c. If f changes sign from positive to negative as x increases through c, then f has a local maximum at c. If f prime changes sign from negative to positive as x increases through c, then f has a local minimum at c. If f prime does not change signs as x increases through c, then f has no local extreme value at c. And that's like when we saw this bad boy. Let me draw it a little bit better. There was a point when our derivative was 0. But it didn't change sign, right? It's increasing, and it's still increasing. So using the first derivative test, consider the function f of x equals 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1. First, find the intervals on which f is increasing and decreasing, and then identify the local extrema of f. So we do just like we did before, and we find the critical points of our function, and then split our real number line into those intervals. So the critical points occur at -1 and +1. So our interval goes from -infinity to -1, from -1 to 1, and then from 1 to +infinity. Now we pick test points within those intervals to determine whether they're increasing or decreasing. Once I pick those test functions, I know that when f prime is less than 0 from -infinity to -1, but f prime is greater than 0 from -1 to 1 and from 1 to +infinity. So I've got a function that looks like this. And when we get to section 4.4, we're really going to tie everything together